we're starting here at MERL. The Technology Strategy Committee is bringing in interesting people from academia. Hopefully we'll increase our collaboration with academia and generally enrich us with new thoughts and new ideas and things. This will be about 2 talks per month throughout the year. With that, I turn it over to Arvind, who's head of the Technology Strategy Committee and leader of this effort.
Thanks, Dick. So we are very happy to have Professor David Bergman give the first talk of our seminar series. David has been a long-time collaborator with MERL. He's right now an associate professor at the Business School of University of Connecticut. David's work focuses on developing novel algorithms for large-scale automated decision-making, and he's applied his research in a wide variety of industries and has an impact on these industries as well. He's a leader in sports analytics and is a 2020 DraftKings Fantasy Football World Champion, and he will share more information on this in this talk. So just a few points before we start off the talk. So the talk is being recorded, and I'll be moderating the session. So please mute your microphones for the majority of the talk. Raise your hands on the Teams app, and I will interject on your behalf at an appropriate pause in the presentation. With that, I turn it over to Professor David Bergman.
Thank you for the introduction, Arvind, and thank you also for the invitation. I'm very happy to be speaking and honored to be the first person in the seminar series. I'll be talking about something, that I love to do, which is sports gambling and applying math and analytics to sports gambling. I want this to be kind of a fun talk, so please do interject with questions through the chat. Happy to answer anything you have now or after the presentation. Just let me know. So great. So I think you can probably see my screen now, right?
Yes.
Okay, great. So yeah, the title of the talk will be Integration of Analytics Techniques for Algorithmic Sports Betting. And I'm going to show several different applications of it, dive a little bit into some work that me and Arvind actually have worked on, and talk about how it applies to one of the sports betting pools. So here's a brief agenda. We'll talk about just what a sports betting pool is, and then we'll talk about how you can model complex objective functions in decision problems using neural networks. So those are kind of 2 different things, but then in the end, I'll show how we use the methodology in the second bullet point to solve problems in the first bullet point through some real-world applications. So yeah, let's start with just the sports betting industry. It is growing at a really kind of ridiculous rate. Over $100 billion is wagered annually in sports right now. Some people estimate it is much higher than that. Just in the NFL alone, so the National Football League in the United States, it's about 95 billion. But again, I'm sure it's much more than that. Estimates go over to 400 billion. Part of what's driving this substantial growth is the fact that lots of legislation is easing for online sports betting. So more and more states are allowing online sports betting, and that's happening at a very fast rate. It's because there's so much revenue to be had by the people that are offering the competitions. And so, yeah, it's becoming a very popular thing. Names like DraftKings and FanDuel are becoming part of just what you see when you watch a sports game online. And a lot of that is driven by the fact that so many people are interested in this industry. Now, what I'm mostly interested in is not trying to bet on necessarily the outcome of a game. So a team is going to win or more by 4 points or something like this. I'm mostly interested in betting pools, and I'll explain what they are. And they encompass quite a significant portion of the sports betting industry. So what is a sports betting pool in general? So what happens is you have a competition, and participants can elect to join that competition. Here I've depicted 3 different participants. Now, the participants are generally able to purchase entries to join a competition, and the size of the number of entries and the cost per entry really varies depending on application. But essentially, a participant can control any number of entries up to some certain limit. What happens then, after they've made their picks, is that the entries are ranked based on their actual performance in sports games that occur. Now, that can be based on player performance or sport performance or whatever, but generally speaking, the entries have to be locked before the games proceed. The games then start, players accrue points, teams win, whatever the case may be. You get points based on how good your entry performs, and we'll talk about what entries might look like. And then what happens is the payout depends on how good your entries perform. So if this example occurred, the blue person came in first, third, and sixth, as I show. In that case, this blue participant would have made $5,000 on their first place entry. Their second entry came in third place, so $1,500. Their third entry came in sixth place, so $250. And then you subtract the entrant fees. So this person, should they have performed this well, would have earned a profit of $6,732, if I did the math correctly. Now, that's just one example of how a pool might look. The tournaments can be really structured in a variety of ways. Here I've shown 3 different types of tournaments. The first one shows kind of a high-cost single entry. So in this case, you can only, as a participant, enter one entry. There can only be 12 total entries. So 12 different participants can only submit one entry. And the cost per entry is $1,500. That has payout structure A. Of course, not everyone's going to make money, but the top 3 placing people in whatever the tournament structure is and whatever sports game you're betting on get the payouts first, second, and third. You might also have a more large competition, again, only where a particular participant can only enter one entry, which is what you see in the second row here. And maybe the cost is $12 and you see payout structure B here. So first place would be able to earn $900 and so forth and so on. They also have much larger tournaments, like what you see in the third row, where each participant can maximally enter 150 entries into whatever the competition is. And again, I'll show you some of those competitions. Here, you can only have a total of 5,098 entries. You can have any number of participants that enter that, but each one up to at most 150 entries. And the cost is $6. Should you be the best out of those 5,000, you get a payout of 5,000, and then the payout structure goes down. I think the important thing to notice from this slide is that the payouts are typically very top heavy. Generally speaking, if you shoot to be number 1, that's how you make a lot of money. If you miss number 1, you might make some money, but shooting for number 1 is really kind of the goal of a lot of the sports bettors. Okay, so that's the general structure of a sports betting pool. Are there any questions so far? Is everybody okay so far? Okay, so I've worked kind of on 3 different applications here. Let me show you those 3 applications just so you can see how diverse these competitions can be. One is NFL Survivor Pools. That stands for National Football League. This is a really, really top-heavy competition. What I mean by that is that an example of a structure is there might be 100,000 entries, each costing $5, and a person can purchase maybe 20 entries. And really, the winner gets the entire prize pool unless there are ties, whereupon they split the entire $500,000. How does it work? So an NFL Survivor Pool works as following. You have an NFL season, which it's important to understand the structure of the football season. Generally, how it works is there are 32 teams. They play games over 17 weeks in different competitions, one against each other. And each team basically plays every week, with the exception of their bye week. But you can think of every team playing essentially every week. And it's a 17-week schedule. A survival pool is the following. Me as a participant, I buy an entry. When I buy an entry, for that entry, what I have to do is I have to select one team to win in each week of the NFL season. Should that team win, I can continue in the pool. If that team loses, that entry is out and I'm no longer participating in the pool. And the goal is to have the entry that lasts the longest, and then you win the entire pool. So here's an example if you had 4 participants. Maybe in week 1, participant 1 picks team 1, participant 2 picks team 1, participant 3 picks team 3, and participant 4 picks team 7. Okay, great. Suppose they all win. They all get to go on to week 2. Now, the caveat is that you can no longer pick the same team more than once. So because team 3 was selected by participant 3 in week 1, they could not pick team 3 again in week 2. And maybe team 3 is a very good team and team 1 is not as good, but they didn't save anything for later on. And so now they get eliminated because suppose team 1 lost. You continue in this fashion until all of the participants, except for 1, have been eliminated, meaning one of their teams have lost, and or it's the end of the year, whereupon you split the entries. And so that's how the NFL survival pool is structured. You can also play other sports games, but it's definitely most popular in the NFL. Okay, so participant 4 would have won. So let's think about the objective function here, right? You can model the objective function and declare it in various different ways. But really the goal is to maximize the probability of lasting the entire season. Because should you be able to pick a winning team all the way up to and including week 17, you are either going to be the sole winner of the entire pool or you're going to split. And more commonly than not, there's more than just one person that makes it all the way through to the end of the season. So really your goal is to last until the end of the seasons. And participants, and what are the constraints on your decision making? Well, participants can select each team at most once for every entry. So what I want to show you is the common thread between all three of the examples I'm going to show. For this example, if I think about the single entry decision problem, suppose I have a probability for each team to win in each week for the entire season, which you can always estimate through a variety of ways. Your goal is to pick a team each week, so that's what the XTW represents, a binary variable, whether you select that team or not in that specific week. You can only pick any team at most once, that's what this constraint, the second constraint, does. And then you want to maximize your probability of surviving, which is really, you want to make a product of the variables, whether you select them or not. Now, I know this is a little bit sloppy here because actually how you might model this is by taking the logarithms of all the probabilities, which of course, since they're all positive, keeps the objective function in the same order, just like if you're doing maximum likelihood estimation or anything where you have a product that you want to turn into a sum. And then you can solve it through standard integer programming. The problem is super easy to solve if you just want to maximize your probability of surviving the whole season. But what I'm most interested in is this multi-entry decision problem. Because if you think about it, suppose I'm able to buy 20 different entries here. So I am controlling 20 different selections through the entire year. My goal is not necessarily to have all of them survive. My goal is just to have one survive. So now what you have is a really complex decision-making problem where the objective function is really hard to model. And when I say it's really hard to model, it is hard to write out an expression for this. I do have a paper published in Operations Research that shows the objective function as it can be modeled, but it is really large, really complex, and very hard to handle exactly. So the question is, how do you solve that problem? Okay, let me show you another example, daily fantasy sports. The daily fantasy sports industry is really booming. The way it plays is there's competitions every single day. Participants pay an entry fee to enter a competition, and with that, they have to select the lineup. Now, each lineup is composed of actual players in a sports competition and must follow the following rules. So, as I said before, there's many different tournament structures. They may have some tournament structures where it's $6 to enter, some tournament structures where it's $2,000 to enter per lineup, and you get to control as many lineups as the competition allows. And the goal here is that, and the idea is that for each entry that you have, you are given 50,000 fake money dollars for each entry. And with those $50,000, you have to select a collection of players subject to some lineup constraints. And I'm showing this for the basketball competition because I think most people are familiar with basketball and some of the things that and the stats that people care about. And so if you look here, this was a competition that I played in that you had to select 4 different entries. With each one of those entries, one of which is highlighted in orange here and shown on the right, you have 50,000 fake dollars. The better players cost more. The not as good players cost less. You have to stay under $50,000 though. And you see their respective salaries here. So Jokic here has a salary of $10,500. Again, you have $50,000, so that's quite a significant chunk of that fake $50,000. But then all the way down to someone like Bertrand's, who's only $3,900. And there's various rules, right? You have to pick 8 players, and you must include players from 2 different NBA games. And the 8 roster positions are as follows. So you have to have at least 1 point guard short, and so forth and so on. And so the goal is that you have to pick this lineup before the games begin. The players accrue points based on how well they perform. And based on how well they perform, that's the score that you get. So in the 4 entries I selected, the actual points that I got from these people in the fantasy sports game was 289.75, 289.0, 258.25, 221.0, and that's the ranking that I received. The points you get for each entry is based on real game statistics again, and you don't know, of course, what their statistics will be that night until they play. Of course, you can leverage data for building predicted models, which is what people do. And these are the points that you get, just to give you an example. So in basketball, you get 1 point for a point made, 0.5 points for a 3-point shot made, and so forth and so on. So you have to pick a collection of 8 people subject to lineup restrictions that you believe will score more points in these fantasy points than any other lineup that is selected by other participants. So how can you model the objective function? And there's many ways of modeling the objective function. If you want to think about the most basic thing one might try, it's to maximize the expected score. So that's your objective function, let's just say. Again, it can be a little bit more complicated, but that is generally one way of doing it. And what are your constraints? Well, you have some lineup restrictions. How does that look for the single entry decision problem? So what you would do is you would calculate the expected number of points that everybody will score. You have a decision variable for each player, and you maximize the sum of the expectations, and then you have lineup restrictions. This is a really, really, really simple integer programming model, which Gurobi can solve, or any other commercial or even open source integer programming solver can solve in essentially 0 seconds. But again, let's go to the question that I actually care about. What if you are controlling more than just one entry in the competition, like 4 of them, as you saw on the previous slide? One way of modeling your objective function there, and it's not exactly what, for example, I do, but it's relatively close and something I've tried before, is that you want to maximize the highest scoring selected entry that you have. Not necessarily that all of them will perform well, just that one of them will perform well. And the reason one might do that is because in this competition, where I came in 10th, 11th, 49th, and 90th, I got $170,000 in winnings. But if you came in first place, you would make $1 million. So it's clear that if you get the top scoring entry, you are going to be a very happy person. And so the goal is to maximize, potentially, the expected value of the maximum scoring of your collection of entries that you have. Because there were 100 people in this pool. Suppose instead of having my top one in 10th and my last one in 90th, I had my top one in 1st and my bottom one in 100th. That would have made me exponentially happier because I would have made so much more money in revenue. This problem, however, is very computationally difficult. And it's so computationally difficult that even writing out explicitly the objective function, if you were to assume that the players are normally distributed, is essentially impossible, and the problem becomes very intractable to solve, at least in an exact way, using an exact model. So it's very hard. Here's another example of a multi-entry sports decision problem, which is challenging, but the single entry problem is not so hard. Before I go on to application 3, any other questions here? Okay, now let's go on to March Madness, which is another.
Oh yeah, sorry.
Please. Yeah.
Is the reason you're not doing the expectation over all the 5 entries say that it's even harder, basically?
Well, so the goal is not just to maximize each one of them individually. It is to
I mean, instead of maximizing the max, you could maximize the sum, the expected value of the sum, but I assume you're not doing that because it's even harder to do than this hard problem.
Well, actually, maximizing the sum would be easy because the best single entry would just be replicated 4 times. Because if the best one has expected value 100, the second best one has expected value 99, and so forth and so on, the best sum of expectations would just be 100 for each. Right?
Oh, okay, but you're maximizing the first place. I mean, like, I guess I'm saying, why not maximize how is maximizing the amount you get from one better than maximizing the amount you get from all? And I guess you're saying because what? Then you would just multiply Why isn't maximizing the amount of money you get out, expected value, the best thing to do? That seems counterintuitive to me.
Okay, that's a great question. So if you could model the profit of a selection, then of course you would pick the highest profit solution and you would enter it as many times as you could. Several problems there. If you want to model the profit, that depends on how other people pick, right? Because you have to become first place out of, or you're going to be ranked based on how you do, based on how everybody else picks as well. So that is one problem, because I don't know what everyone else's selections are going to be until the games start. And so I'd have to be able to model how they pick, which of course you can do, and it's something that I do also. But it's very hard to do that because people, first of all, change their strategies constantly, at least the very good players. And secondly, every single competition, the salaries are so different and it's really hard to tell that. So modeling your profit is it's an even harder problem, right? Again, because people are constantly changing their strategies. And yes, if I could pick the best possible profit entry, I would buy in as often as I can. I would buy in as many entries as I can and just replicate that one every single time, because that's the biggest return, the biggest profit entry, but that's hard to do. Secondly, that leads to a very high variance solution, because the highest profitable entry might be something that comes in first only, especially for the very big pools, once in every, let's just say 100 days, but loses money on all other 99 days. Now, although the profit might be good, that takes you 100 days. And then what happens is your profit swing will be too much. So that's a problem with doing that as well.
So when you say maximize the highest scoring selected entry, can you just say one more time then what that is doing?
Yes. So what it's doing is it's saying you are going to have 4 entries. Let's not try to make sure that all of them do well. Let's try to find a solution among all 4 of these so that one of the entries shoots off as high as you possibly can. So it's an order statistics problem, right? I don't care about all of them necessarily. I care about just one of them performing very well. I don't know a priori which one of them will perform well, but I want at least one of them to perform very well under as many outcomes as I can cover.
Okay, now I see why that's a hard problem to write out. Thank you.
Sure.
What is magnitude of n here? How many players do you have to choose from?
So
from.
Yeah, totally depends, right? So there can be competitions which are based on 15 games, where in the NBA, maybe there's 8 people you might actually consider. So, you got hundreds of players, but there are also competitions on single games, which they have a little bit of a different rule. So it increases the lineup diversity. You have to pick a captain and all this stuff, but it goes all the way from a single game up to, 15 games. If it's a baseball competition, there's oftentimes 15 game competitions. And there, the possible people, you've got basically a pitcher per, you've got 30 teams playing, right? So a pitcher per team, and then also the 9 batters on the team. And there's other complications too, because there can be staggered start times, and so only part of the lineup blocks at the beginning and so forth and so on. But the basic structure is as I'm showing here.
Okay, so it's a few hundred, but not a few thousand.
It's not a few thousand, it's a few hundred, yes.
Okay. So enumeration is not going to solve the problem easily, but you've run a bunch of simulations. Okay, I got an idea. I'll talk to you later.
Yeah, sure. I mean, you can definitely run simulations and try to optimize over them, but one thing to keep in mind is that the variance is really high of these players. And so the number of simulations that you'd have to simulate in order to directly optimize over can be prohibitive. It's challenging because, again, the variance is so high. So in order to get like a pretty good estimate on what's going to happen, you just have to simulate a lot, which will lead us to the solution that I will show you later on today.
Matt?
Yeah, so actually I'm surprised that the multi-entry decision problem isn't maximizing the minimum payoff amongst your entries, subject to some diversity constraint between the entries.
Some people try to do this, right? But there's again, once we say maximizing your return, okay, the challenge that you'll get to is that it's very hard to model your return because you can try to see how people select, but you're playing against people that play every night, me included, who change their strategy constantly. And you can see it, right? Some night they pick like a core of people on every lineup for some reason, and they hope that, you know, that core does very well so they can shoot all their entries. Sometimes they get a very widespread solution. And so trying to predict what these other very good players are going to be doing is a very hard thing, in particular because they actually change their strategy from game to game.
So the score is not a good proxy for the return?
It is the proxy, but then if you're just maximizing the minimum score, the problem is that you might end up with a situation. Let me show you the payout structure one more time. So let me show you the payout structure here. I wish I had it on the screen. First prize is 1 million. Second prize is 300,000, and then it goes down. So getting just one all the way up there, it really means a lot. Now, you may try to do that, and that is a solution that, you know, you try to maximize the minimum or something like this. That can work, but another thing to note is that the payout generally stops after about a top quarter or a top fifth of the entry. So if there's 100 people in the pool, only the 1st through 20th. So if you maximize the minimum, you end up with a lot of lineups that might be around 25th, and then you might not even get any payout, right? And so it is pretty tricky. But these are all things that, of course, you know, and I'm not, you know, this is not as simple as my objective function, clearly, but it is, you know, I've tried a bunch of these things: maximize the minimum, maximize the, you know, the second highest of the scoring entries, all these other kind of things that you might think about. Yes, these are all valid points, I think. But regardless, even if you were trying to maximize the minimum, that would be a very hard problem too, because that's, again, an order statistic based on how they all perform. And I mean, if you're really trying to maximize the minimum without considering anything else, you actually, again, are going to basically come up with a solution where you just replicate all 4 lineups at the same time, which is fine, maybe. The only challenge is that then you have huge, huge variance in your payout. And you may have to wait 100 competitions before you get one really big hit.
Sure.
Now, the big hit might be profitable, sure, but you have
machine learning, though, there's
too.
an attempt to have some constraint on the diversity between the entries so that you get a spread sample of the mode of the distribution.
Correct, because in any betting context, whether you're playing poker or daily fantasy sports, one of the most important things is bankroll management. And because the problem is, once your bankroll rolls out, you're done, right? And so as your bankroll goes down, you have to limit the competitions you go into based on this Kelly criteria, which is a long established betting thing. Well, at least if you're trying to do it for optimal long run profitability. And so the problem is, like, if you can somehow reduce your variance, that can also help. So yes, these are all very good points. I agree wholeheartedly that the objective function is perhaps not perfect, but it is some proxy anyway of what your probability of being the top is, which is the highest paying one. So anyway, yes, agreed. All good points.
One more, maybe one last question, David. Bill?
Pass for now.
Okay.
Awesome. Yeah, and please interject with any questions. I think these are all very good questions. And again, the decision-making problem is actually more complex than this. One example of why it's more complex is that suppose you're playing a baseball slate. It generally starts at 7 o'clock. There might be 5 or 6 games that start at 7 o'clock. Then there's some games that start at 8 o'clock and some games that start at 10 o'clock. Part of the challenge is that the 10 o'clock lineups are not set yet. So you also have to take into account some issues there because you don't actually know with 100% certainty who's going to play. And there is quite variability, and it's really hard to predict who's going to play every day. But also, when you set your lineups at 7 o'clock, you have to set a full lineup, but you're free to change any player that is playing in a game that hasn't started yet. So now you also have to consider the probability of people not playing and all this other stuff. So it's, yeah, this is the basis, but yes, it also gets more complicated beyond that.
Okay, what's the magnitude of the bankroll versus the magnitude of the cost to get into an individual game?
So there are competitions every single night that are single entry and cost $25,000. There are competitions almost, I mean, in the NFL, it's kind of bonkers. There's competitions to fully buy in are $100,000. So $4,444 for 26 entries. So that's about $115,000 just to enter the competition. Of course, $1 million prize up top. And then there's some competitions that are 50 cents, 25 cents, $3 times 20, whatever. There are, I think, probably 400 different, or for NFL Sunday, National Football League, there's probably 400 different competitions that DraftKings offers, just DraftKings, not including FanDuel. And, you know, for a standard baseball night, maybe there's 100 different competitions, and they're different ones, right? There's some of them which are single entry and not top heavy, where, you know, there's maybe 11 participants and the top 5 score, as opposed to, and they just split the money, right? So the service takes about 10% out. So let's say it's $1 per person with 11 entries. So the service takes $1 out. So there's $10 in the pool. If you win, you get $2. So there's a lot of competitions like that. The higher cost competitions with the really large prizes are all these kind of top heavy competitions. And it also goes all the way up. You know, last week they had a competition with 1 million entries in NFL, 1 million. So, and you could enter at most 150. So, and it fills. There are over 1 million entries in that competition last weekend.
How much was it to buy in an entry?
For that one, it was $5. The standard $1 million up top prize on NFL Sunday is typically $20 per entry. And it's 150 entries. And there's about 250,000, a little bit more, because that's where they take their rake, right? And so, yeah, I mean, there's like, you know, $2.5–3 million in the pool, top prize $1 million, and then it quickly goes down after that. So in that case, the top prize is actually something like, you know, 40 or 30% of the entire buy-in that's awarded as prizes.
Okay, so bankrolling size is not that big an issue. Thank you.
Yep. But of course, if you're going to go for the smaller competitions, you can't win as much, right? Because, well, those are very hard to win, right? So if you want to make a lot of return, you want to be playing, at least for me, the way that I play, I want to be playing in competitions that are not that massive. I mean, it's really hard to win a competition with 267,000 people. But when you're playing a bunch of competitions with, you know, 100 people and you have 3 entries, or 1,000 people and you have 20 entries, or whatever the case may be, you can win those a little bit more frequently. But if you have a high variance solution, your bankroll does go down quite substantially, quite quickly. And so then you have that issue that you just can't buy into the ones that have top enough prize that are realistic to win at a fast enough rate. Cool. Good. Any other questions?
No other questions. Keep going, David.
Awesome. And I'll give one. Anything else? Did someone else have a question?
No.
Okay. Great. So let's go on to March Madness, which is yet another pool. Okay. So billions are spent on wagering per year for March Madness. You know, just millions and millions of people play this all over the country. March Madness is a tournament based on college basketball. There are actually more than that, but let's just say 64 teams that make the tournament, just to simplify things. And they play in a single elimination tournament. So 64 teams, they all play in the first round. You see the 32 teams on this side, 32 teams on this side. There are actually 4 different quadrants of 16 teams. I'll talk about that in a moment. And then what you have is you've got just a single elimination tournament. So after the first round, you get down to 32 people. Second round, 16 people. Third round, 8. Fourth round, 4. Fifth round, 2. And then the 6th round is the tournament champion, and that's 6 rounds. And the goal of a participant in these pools is to pick entries so that you can score as many points as you can. And the scoring of the point depends on how many games you correctly predict. What you're given at the start of a March Madness tournament is you have the seeds of each team in each quadrant. So you have 4 different quadrants, 1, 2, 3, 4. In each quadrant, the teams are kind of ranked 1 through 16. Note that that also dictates the potential matchups as the tournament progresses, because in each one of the quadrants, the 1st and the 16th team play the first game. The 2nd and the 8th and the 2nd and the 15th team play a game, and so forth and so on. And so you actually know, if you make it to round 3, who your potential opponents will be in round 3. You also know, of course, the performance of teams over the season, and that provides data to estimate win probabilities. And I'm not going to go into the estimation today, but that's something that's studied in the literature and lots of articles online. They use the various statistics that might work. I mean, of course, the prediction in sports is never perfect. You can only really get up to 70 or 75%. But anyway, you can get some probability estimate for any possible matchup. How does the scoring work for March Madness? In a typical setting, each entry is scored based on given winners selected. So receives 2 to the R-1 points for correct selection in round R. So as the tournament proceeds, you're able to score more points if you get the correct entries. So suppose that this was a very small tournament of 4 teams. Just to explain how it works, you've got team 1 playing team 2, team 3 playing team 4. Suppose that you decide that you want to pick team 1 to pick that matchup and team 4 to win that matchup. And then you have team 1 against team 4, and suppose you pick team 1 to pick that matchup. Now, suppose this was the actual outcome, that team 1 won its first game, team 3 won the first game, but then team 1 won. The entry submitted would have scored 3 points because it correctly picked 2 of the 3 games, scoring 1 and 2 points respectively, and the entry would have received 3 points. So that's how it goes. And of course, the goal, as most sports betting pool is to kind of pick the best one you can. Note that Warren Buffett offered $1 billion to anyone who could select the entire 63 game, 64 team, so apologies for that typo, tournament correctly. Of course, no one did, because it's basically impossible to do that. But the goal is to pick as many as you can correctly, weighted by the round of the game. So again, if you're playing this, you're going to say, yeah, the subjective function is a little bit suspicious. And I agree with you, right? You can actually model this in many different ways. And actually, one of the most important things in March Madness is to consider location. So if I'm playing against a bunch of players in Boston, suppose it's a local pool, I should never pick any of the Boston teams to do well, because everyone is going to pick the Boston teams. So you want to hedge against that. And so if something else happens. So, and there's also variance that you might want to learn and all these other things. Okay, agreed. But one possible objective might be to maximize your expected score. And maybe for one entry that really won't do much for you, as you go up to 20, 100, 1,000 entries, this might actually work well. But anyway, suppose that's your goal. You just want to maximize your expected score. So this was studied by Ed Kaplan, who I believe was a former Informs president. And this is a paper from 2007. And they showed how you could solve this problem. You can either use a basic integer programming model or some kind of basic dynamic programming model. But anyway, easy calculation. Okay, easy calculation. However, if you look at the multi-entry decision problem, well, again, suppose you don't care about having all of your entries do well. You really just want one to shoot off super high, which makes sense because you really only get paid in March Madness if you score really towards the top of the pool. That becomes super hard because you've got so much correlation between the entries. Because if you pick the same team to win, then there's a lot of correlation in how those entries perform. If you pick opponents, then there's kind of this like negative correlation. And then if you pick neither of those teams because you're picking different teams, there's still some correlation in how the score is going to happen, because if that does well, the other ones, of course, can't do well because they selected someone else to win that game. But if, here we can express the objective function. It's expressible. I've sat for quite a while just trying to write down a mathematical formulation for this problem, and it is really, really hard. I don't know how to do it, for example, because I mean, you can do it in a very exponential way. Of course, you can just say, here's all of the possible selections for all of the possible entries, but there's 2 to the, 63rd entries per 2 to the 63rd possible selections, and so it becomes quickly intractable. Okay, so what's the commonality? You've got a single entry optimization problem, which is kind of easy, and the multi-entry problem is really hard, not just computationally, but generally hard to even mathematically model. How do we then seek to solve this problem? One way is to train a neural network to predict what the objective function is for any solution. And then what you do is you select the features that will optimize for the output of the neural network. This is a kind of related to a project that Arvind and I have worked on, which is how do you embed neural networks in a decision optimization problem? And let me quickly motivate that. I mean, we're already at 1:43. Arvind, is it okay for me to go up to 2 o'clock with this presentation?
Yeah, sure. Please go ahead.
Excellent. So let me just explain a little bit about the origins of this solver that we created and just this overall decision-making context, which we're not the first people ever to think about it, but how we formalized it, and then talk about, for March Madness, how one might solve it. So let's think about a marketing budget allocation problem. Very simple. You are thinking about how much to advertise in multiple different channels. You have a budget, and X1 through X3 might be how much you allocate. And suppose one could somehow put an estimated return based on the amount that you market and any other kind of decisions that you have to make, which for each one of those allocations might be F1. And these can be tied together too, right? I'm not saying that the newspaper plus TV doesn't have some effect. I'm just saying for this exploratory example, just assume that you get some type of benefit from marketing via TV, newspaper, or online. Now, what would be a model for solving this problem? Well, you have your budget, you've got your 3 variables, and you have to decide how much to allocate to each one of these streams of advertising. If these Fs are estimated through linear regression models, this problem is kind of easy, and actually the solution would not be very interesting, but the problem is kind of easy. You're maximizing, and of course the coefficients in the linear regression model would dictate what the coefficients of the variables are here. And all of a sudden you have this type of problem, and you have this budget constraint. You might also limit the budget for each one of the streams of advertising, but anyway, this is what it might look like. But suppose instead of estimating the revenue or profit, whatever, the return from any one of these advertising methods, you actually used a radial kernel support vector regression, or a neural network, or if it was a logistic regression model, if you're trying to predict some probability based on the features that you're going to produce. Now, how do you solve a problem like this? And the problem that actually spurred me to think about this was a project that I was doing with a company, well, actually with a large public university. And it was a college student enrollment management problem. And they came to me with the following question. They said, suppose that we have 20,000 past student records for students that were accepted to our university. We have their SAT score, their GPA score, and actually a bunch of other features. And we also know how much merit-based aid or scholarship we provided for the students. Now we have decided to accept for this incoming year, let's just say 1,000 students, just throwing out some random number. How much aid should we offer to each one of the students to maximize the expected size of the incoming class? So what you would do is you think about kind of fitting a model for predicting what your enrollment probability will be per student based on the features that you have available, SAT, GPA, and then the amount of money that you give someone. Of course, the more money you give someone, the higher the probability of them enrolling, of course, with some limits, right? But you have data that you can estimate this, right? And you can estimate it with a neural network, you can estimate it with a logistic regression model, you can estimate it with whatever mechanism you want, but you could pre-train a predictive model for estimating the probability for enrollment. And then you say to yourself, okay, let's maximize the amount of people that end up coming. And you can model it as you see here. You have a variable y, which represents for every student the probability that the student enrolls. That y depends on the amount of aid you give, which is this x sub I, and the pre-trained model that you use to predict the enrollment probability. In a more high-level view, just to skip forward a little bit quicker, what you can do is you can pre-train a neural network based on your previous data using the 3 features you have to predict your enrollment probability. Now, for every person that you've accepted, you have their SAT score, you have their GPA score, but now you have a lever that you can choose, which is what is your scholarship? And suppose that you want to maximize the number of people that come into your university, which is part of what universities try to maximize for. There's actually other things, but let's just say that was a simplified objective here. What you would do is you'd maximize the sum of the y's, because that's the probability, so that would give you the expectation. But the output of the neural network depends on the features. So that's what, the project with Arvind seek to solve that we worked on, which was how do you solve a decision optimization problem where you have sometimes thousands of embedded neural networks of various sizes. Of course, the larger the neural networks, the harder it is to solve this thing. But how can you solve this problem in a systematic way? Where the features are variables in a decision problem. Here, the x's and the y's are outcomes of the prediction. Let's talk about how we can potentially apply it to March Madness. This is kind of ongoing work with a student that I'm working with and also with a few other colleagues. So suppose that you want to maximize the expected value of the maximum scoring entry. Again, I encourage you, if you're interested in sports gambling in March Madness, to try to write out an expression for the expected number of points, right? Again, you get 2 to the r-1 points for every round that you pick right. Try to write the expression for the objective function here, if you were trying to maximize the expected value of the maximum scoring entry, or really anything else, maximizing the expected value of the maximum score plus variance so that you can kind of hit a top thing sometimes, or anything. It's really hard to write down mathematically. But one can do is potentially train a neural network to predict the expected value of the maximum scoring entry using simulation. And I think someone kind of pointed at this, right? One could simulate a bunch of times and optimize, right? The problem is the number of simulations you need makes the ensuing optimization problem essentially impossible to solve in any computationally effective way. But if you're able to train a relatively small neural network that's able to predict the aggregate, is fit to predict the aggregate or average of what a bunch of simulations do, I don't care if it's millions of simulations, then what you're able to do is create a proxy for the objective function and use it for selections. So let's talk about the features that we use here. In order to calculate the features, I have to use some probability estimates. And let's just say we have P sub GT, which is the probability that team T wins game G. Note that you don't even know, even if you tell me that team 1 is going to play in the 3rd game, which of course presupposes that they win all their games up to that round. You don't even know who they're going to play, but through some fairly simple recursion, you can calculate these probabilities, given probability estimates for every pairwise game that might occur. The number of features that we use is, if we have E entries, 63 times E, there's 63 games in a tournament, plus 63 times E choose 2 features. And let me explain what they are. The first collection of features are, for every entry in every single game, you calculate 2. So again, I'm just trying to produce a neural network that can predict the expected score of the maximum of, let's just say, 2 entries. You have for each game the 2 to the round -1, so that's just the score of that thing, times the probability that that team will win that game. That is the first collection of 63 63 of the features for each one of the entries. Then you also have an indicator for whether or not the entries have the same team selected to win in each of the entries, because you want to make sure that you are somehow accounting for the fact that you might pick the same team in 2 different entries. So how does it look? Suppose that you have 2 entries, entry 1 and entry 2, and suppose you're filling out 2 of these brackets. there's a linear mapping of the solution to the entries. The first 63 times E entries look as follows. You can just, if you had the solution, you could linearly or just calculate these features, right? It's just you pick your selection and you calculate the probability of them winning that game, multiply by the score that they would win if they won that game. You do that both for solution 1 and solution 2. So those are 63 times 2 entries. And then you also just have, again, 63 entries if it's only 2 entries, right? And you just select. So actually, I was wrong there. It's actually 63, choose E minus 1. But OK, so here you just have an indication of whether the 2 entries are the same in each game. You pump that through a neural network that gives you an estimate of the expected score of the maximum among the entries. So that's the goal. We want to train a neural network. Suppose we're just doing the 2-entry solution, which has 63 plus 63 plus 63 entries. Those are the features. You pump it through a neural network, and it provides an estimate for the expected value. And then what we do is we formulate a decision problem where your decision variables are simply the winner of each game that you're going to pick. You have some feasibility constraints to ensure that if you pick a winner in round 3, they also won round 2, but that's easy to do. And then you try to maximize the output of this neural network. How do we train the neural network? So for these experiments that I'll show you, we randomly draw 160,000 E-entry solutions. For each one, we calculate the average value of the maximum scoring entry for 100,000 possible outcomes, right? And so the real beauty of this kind of modeling construct is that you can simulate a lot of times. And then you use the neural network to find out and figure out and encapsulate the information that's contained in those 100,000 solutions. And then you don't have to optimize over the 100,000 simulations. You just have to optimize over the single neural network that you're going to get. So that's how we train it. We test it on randomly drawn 20,000 solutions. Again, you calculate the average and you see how far it is off. Now, again, I don't actually know the true value of any solution because it is too hard to calculate. Just to calculate what the expected value of the maximum scoring entry is when you give me even 2 entries, but I can estimate it. So what you'll see here is the neural network accuracy. What I'm showing here, and you can focus on the bottom line, and which is replicated here for the most important things, okay, is I show 2 different measures of accuracy. One is the common MAPE, so the mean absolute percent error, and one is for 2 and 3 entry solutions, how often the prediction gives you a solution that is within 2 points of what an out-of-sample collection of samples would predict on average is the solution quality. What you see is that happens 99% for the 2-entry neural networks. The neural networks have 2 hidden layers with 32 nodes in each, if I'm recalling that correctly, but it's something along that order of magnitude. And then you see the mean absolute percent error, which is, the highest possible score is, I think it's 190 something, 192 maybe. And so, a 0.67% MAPE is about a 1% thing, 1 point approximately on average, and then 0.91 is maybe a little higher. But that's what the kind of estimated quality of these neural networks are. It's probably a little bit worse only because we don't know really what it is. We can only estimate what the expectation is based on a lot of samples. But anyway, you don't have to actually hold those simulations when you're optimizing. You just have to embed this neural network in the decision problem. So what's the quality of the solutions? I am first going to show you the quality of the expected value of the solutions outputted, again, as measured by a new collection of simulations. And then I'll show you what the average actual solution values are for multiple different approaches. And I'm not going to go into all the competing approaches, but so Janos is the one that we are using for our approach. We compare against an optimization model that has 10,000 simulations or 100,000 simulations, or a kind of simple IP where you add some diversity constraints, or a genetic algorithm that we tuned. Anyway, we competed against 4 different solution approaches that we could possibly think of. In expectation, we find that for the 2-entry solution, Janos gives about a 95.15, whereupon the best competing approach gives you a 94.41. When you go to a 3-entry solution, 100.42 versus 96.21. Now, that's just an expectation. If we look at what the if you actually made those decisions, what would have happened? And again, you don't have so much data, right? So there's clearly going to be some mismatch between what you score and the expectation. And you would assume, you know, in any given points, if the scores are in any given year, if the scores are higher with one approach than the expectation, it would be with other approaches because it's just an easier outcome in terms of favorites winning more or less. But anyway, here is the average scoring value over all of the competing ones per year. You can focus on the bottom or just look at the highlighted things here. And you'll see that, you know, Janos, the average solution value for 2 entries is 105.83, for 3 entry, 108.17. Again, this is what you average would have scored. And then you also see the best competing approaches. And, you know, I think that, you know, this is a hard problem. I think if you're just doing 2 entries, it's a bit complicated to really get in first place, depending on how many people you're playing against. But anyway, it shows how this decision, so it shows 2 things. Number one, it shows how this decision-making process using this solver, or at least solution approach, can work. And it also shows that, you know, you can really embed a bunch of simulations into one relatively small neural network in order to just take all that information so that you can make your decisions. Yeah, and I think that before I conclude, I'll show you a quick video, which will be funny for most of you, I'm sure. Give me a second.
All right, we now welcome in the winner of DraftKings 2020 Fantasy Football World Championship, David Bergman, aka the Whistles Go. Yep, there's the woo. $2.5 million richer, David.
Stop it there. Yeah, so I won the Fantasy Football World Championship. And yeah, I mean, you know, I've been continuing to play and have had, you know, some success. So that's what I wanted to cover. Hope you found it interesting. And yeah, any questions you have, whether it's about the application area or about the methodology, happy to answer.
Thank you, David.
Well, it answers one of my questions, which is, if your methods are so good, why ain't you rich?
Well,
So, well, you answered it.
Petros?
Sorry. Yeah, I have a quick question. I was in Greece recently, and some friends were playing some of those things. And some of them, at least in Europe, seem to have the ability to bet while the game is in progress. Is that something that makes things trickier or easier, or both?
Yeah. So I think there's 2 answers to that. So in-game betting is something that's also becoming more popular. And that is, I mean, there's many different ways in which in-game betting can happen. One of the ways is that, you know, you can bet on the outcome of a game. Like, I want to bet on the New York Giants winning, and then halfway through the game, you can modify your bet depending on how the game proceeds. In the context of daily fantasy sports, it's also important because suppose it's 7 o'clock again for this baseball example. Some of the games only started at 10 o'clock. Now, while I have to submit a lineup that satisfies all the restrictions in the lineups at 7 o'clock, I am free to modify any of my selections for the 10 o'clock games as this proceeds. Now, this is interesting for 2 reasons. One reason, because you don't even know who's going to play in the 10 o'clock game yet, so you want to have the capability of re-optimizing halfway through. But another reason is, suppose you have 2 entries that are very similar on the early games, but you notice that really one of them has a much better chance of surviving over the second one now. By surviving, I mean performing very well. The selection for the remaining players might now be different if you want to maximize how high you might choose, because you might want to kind of float more of the, you know, just variance or expectation or whatever, lower variance or whatever you want to one of the particular entries. So the answer is, yeah, the in-game changes, like while the competition has started, is very interesting and really challenging to do. And I think that provides optimizers quite an edge, actually. And I think that part of the, yeah, I mean, you know, there are some competitions where all the games start at once in daily fantasy sports, whereupon you can't make any changes after it starts, right? But yeah, anyway, so that's some things to keep in mind.
Mike?
Thank you.
Sure.
Just a quick question. I didn't hear you address this, but maybe I missed it. But how are you calculating, say, for March Madness, the probability of Team 1 beating Team 2? Basic probabilities.
Yeah, I haven't got into the estimation problem. There's many different ways that you can do that. There are ELO ranks, which is something that you can look up online. That's just a way that provides some kind of power ranking for teams. But there's a lot of different metrics that people publish for the quality of the solution, the quality of March Madness. I'm sorry, the quality of college basketball teams. And you can use all types of those. And I don't remember the names of them right now offhand, but I can provide you. And again, most sporting events, you really can't predict the winner more than 70%, 75% of the time. It's just the nature of it, right? I mean, there's so much variance in sports. So there are some data sources that people commonly use. Then there's published research on how you estimate the probability. So we just use, we tried multiple approaches, and the quality of the solutions from our decision problem were somewhat independent of what method we use to estimate the probabilities, because I think the estimate of the probabilities actually don't vary so much when you use the different methods out there, but they really don't get any better than 70% accuracy or 75%. Also depends on women. So in women's basketball, you can predict the accuracy much better than in men's basketball. So that's also very interesting. We do have some differences in the quality of the solutions between women and men's basketball, and we're trying to understand that. But anyway, yeah, so that's the short answer to your question.
Jake?
Yes, I wondered what was up with Warren Buffett. Was he just trying to collect data out of the crowd?
I think he just wanted to, I don't know, prove a point that he could pick some sports betting thing that he could wager $1 billion, but he knew he was not going to lose the $1 billion, at least an expectation. Probably just publicity, but I really don't know. Who knows?
Any further questions?
Yeah, I just, as long as no one else is asking, I'm just trying to get an idea of, don't give away any secrets, but I'm just trying to get an idea of sort of what your typical night of, human interest thing. What's your typical night of sports betting? How much time, how do you manage these changing deadlines for the 7 o'clock, the 10 o'clock? Are you watching TV? Are you looking at the stats? Do you have your simulations running for hours beforehand? Just some idea of how that works.
Yeah, I mean, yeah, okay. And I appreciate that you said I'm not trying to, but I will tell you, it depends on the game, okay? Take basketball, for example. The lineups are not known sometimes a minute before the game time, and that's not an exaggeration. So in basketball, you need to have some reasonable model that can run in 30 seconds, independent of how big the model the slate is. Because also in basketball, if there's a very good player like Giannis, okay, he's a very, very, very good player. And it's frequent that he's injured and you just don't know if he's going to play. If he decides if he cannot play, then all of a sudden the entire dynamic of the game changes. I mean, in basketball, it is outrageous how different the projections of other guys get, because this guy can average 30 points a game. And if there's 100 points in a game, there still would be approximately 100 points in that game. It's just the other team has a different distribution in the scores they're going to get. His team has a different distribution in the score. So for basketball, it has to be a fast model. There's really nothing else you can do about it. For other sports, you have a little bit more flexibility. So take football. Generally speaking, the games lock at 1 o'clock and 4 o'clock, if you're talking about the really massive games. And the lineups are somewhat known about 90 minutes before the game time. So you have a little bit more time to run your model, more whatever the case may be, whatever you want to run, okay? But it just depends. And the information I get is from a variety of sources. And again, it depends on the sport because it depends on the need for speed or the non-need for speed. There are projection sites that project scores of players, and if you're not going to even just use them for projections, you can at least use them for news about who's going to play, right? Because if they have a player projected at 20 points, I don't know, whatever the case may be, you can feel pretty solid that those people will play, right? And so, like, I think you can use those data sources for at least information about who's in the game or not.
Thanks. It sounds like it's much more last minute than I realized then, if you're talking about 9 minutes before.
Depending on the sport, yeah. Certainly in basketball. I mean, if you ask my wife, she hates basketball season. That's all I'll say. Yes. It just depends on the sport. Yeah.
Thanks.
Sure.
Hey, thanks, David, for the talk. I was wondering what you think in the future when more people will be using optimization-based approaches. Do you think you would have to start worrying about your formulations need to account for the fact that there'll be others optimizing as well?
There's.
Yeah.
Go ahead. Yeah.
No, I don't know if you have already started worrying about that kind of a problem, or if it's too complex to even think about it right now.
It's definitely not too complex to think about. And I was at the Fantasy Baseball World Championship very recently, and one of the players there, he's a younger guy, but he read some of my work and everything, and he said he's implementing my strategies, and he was really happy, and that's fine, right? And I think just like anything else, I take poker, okay? A lot of the players in daily fantasy sports, me not included, are former poker players. And what happened there is that poker became too saturated with the really good players, I think. And there's basically no question that this will eventually happen, right? I mean, I think that, yeah, it'll happen. It'll take some time, right? Because, I'm showing you the basics, right? But like, it took me quite a bit of time to really understand the right strategy here. It's not just a simple thing, right? I mean, it's complicated, yeah? And so someone would have to spend enough time. Of course, anybody on this call has the technical capability of doing that, but you'd have to spend enough time and really, you have to grow your bankroll and all these things, right? But yeah, I think it will happen. That's clear, that it become too saturated. But until then, I'm having fun, so.
Thank you.
Matt?
So these are all markets of a sort, and in many markets, eventually the market maker finds it disadvantageous to have really asymmetric play. When you have people with huge computational resources, it discourages the novices that are essentially the source of money. And so we've seen this in lotteries where there's extensive effort to avoid gaming the system, but also now in online poker where machines are, whipping everybody, and the players are withdrawing. So when do you expect to see countermeasures?
Yeah, I think so. So in standard online sports betting, I think they'll do it first, right? Because they, as the service providing the odds, don't want to lose money, right? So if someone's better than them, they will no doubt handle that in some way, I guess. I don't know. And I don't know. I mean, I think, there are some people that play this that are very competitive and sometimes much better than all the optimizers are, and they can. Will this continue forever? I'm not sure. I mean, for example, the Fantasy Baseball World Championship, there were only 100 entries in total. I had 5. This other person had 5 who's a math guy. Another person had 4 who's a math guy. But someone that just plays one single entry every night came in first place, and he had 1 entry. And so I think there's still a long way for us optimizers to learn. And I think that means there's even a longer way for us to really take over the industry. But it will happen probably eventually. And I don't know what the response will be, but we'll see.
Dick?
Yeah, I was, it's interesting that the last 3 of us are sort of asking the same question. I mean, I was musing, it does seem to me that eventually people with computational resources and math have got to beat the average duffer. And another aspect of that, it strikes me, is additional investment in computer hardware. So my somewhat facetious question is, well, when will NVIDIA be selling more machines to sports gamblers than they are to crypto miners?
Yeah, what a good question. And I think my answer is you can't make as much money on daily or any really sports betting than you can in crypto mining or cryptocurrency trading either, right? Because there's a limit to the number of competitions you can get into. It's high, but it's not, something as big as the people make on Wall Street or anything like that, right? So hedge fund managers are making way more than anybody in the daily fantasy sports industry, right? And so I think, yeah, that's at least, but of course, yeah, I'm sure that, it will go in that direction at some point.
All right, thanks.
Sure.
Tim, do you have another question?
Oh, sorry, I didn't lower my hand.
Okay. All right. Abraham?
I also forgot to lower my hand, sorry.
All right. If there are no further questions, then let's thank the speaker.
Awesome.